So on December 7th, 1941, my grandparents were living on the island of Oahu. My grandfather was in the Navy, and my grandmother had recently married him, and so they were living in base housing at Pearl Harbor. And that morning, my grandmother woke up and said she needed some things from the grocery, and thought she heard drills running down at the base, but that wasn't anything abnormal for them. And when she got to the store, the radio was on, and had learned, obviously, at that point what was going on. And she said she went home and she was glued to her radio the rest of the day, and actually called her employer the next day. She was a clerk on the base, and went into work the following day to try to help with the situation. So my name is Tricia Veeder, and I came to DARPA because I thought about the impact that strategic surprise had on not just my grandparents, but their entire generation. And the DARPA mission of preventing and creating that strategic surprise was the reason that I came to DARPA. So today I'm going to talk to you about context-aware imaging, which is my current interest at DARPA. And so I'm going to start off with what is context-aware imaging. So this is just a diagram that shows how we do signal processing today. And images contain a ton of information. There is information in the light itself, what is reflected or emitted from an object. You also have the optics signal chain. You have an absorber. You've got readout integrated circuits and electronics. And we gather all that information so that we can come up with an algorithm, which is your set of rules to get to an expected output from the given input, and get to our mission that way. Now, the way this works today, that diagram goes from left to right. And that's great because historically we've had very, very little image information. We had to do it this way because you had to extract every little piece of information you could from every single pixel and every frame that you had. And, for decades, the signal processing people have been telling us, hey, if I could just get Tricia the information that's interesting to me, just give me those pieces, Trish. I don't care about the rest of it. I could get you a better answer, and I could get it to you faster. And so far, we've said no to those people. And the reason is because if you had to have the very specific set of information that they want to get to that faster, better solution, you would have to have 20 different cameras, each doing a very dedicated function to achieve that objective. But what I would like to do is see if we can get this diagram now to go from right to left. So the outputs that we are after, we want to be able to have algorithms that reach back into an image sensor and tell it what to acquire. And to do that, you need to have very tunable signal elements of your signal chain. And I would like to suggest that context-aware imaging is the next step that we need to reduce that 20 apertures, each with very specific functions, back into a single aperture so that we can get to that signal processing goal of being able to do everything faster and better than we do today. So what problem are we trying to solve with context awareness? This should be pretty evident to everybody out there. The cell phone megapixels that you get in your cell phone cameras every year has increased. Both of these diagrams ended 10 plus years ago at this point. And infrared image sensor formats have dramatically changed. I mean, when I started my career, we were very pleased with ourselves to make a 1K by 1K single megapixel array. Now we're looking at much larger image formats, and these are only getting bigger. And then also we're talking about networking these cameras, whether that's a network of security cameras or a network of image sensing satellites on orbit. We want all of those to be networked together. And so the image information that you're getting is only going to get bigger and bigger with time, which means that image data transfer and the processing capability that you need to process all that image data is only going to get worse with time. So what I'm going to introduce next is I'm going to talk about the various elements in the signal chain and how they can contribute to context awareness. So first of all, we'll talk about absorbers. So this is your detector semiconductor material that takes photons and converts that into electrons. Now, absorbers, we've had dramatically different, the last 50 years, even the last 20 years, I would say, are dramatically different than they were previously. We've had quite a bit of development. I think that there is a detector material out there to do almost everything that you would need it to do. We've got multiple bands, we've got good quantum efficiency, dark current density, speed and uniformity of the detectors, and we get these all from a variety of different types of detector materials. I would say that today absorbers measure all bands and they can count single photons. So I can't think of anything else that an absorber would need to do to become more context aware. Do we need anything else for context awareness? Maybe you'll tell me yes, tell me that I'm wrong, but I don't really see anything else that we would do here. So moving on to the readout integrated circuit piece of the signal chain. These have actually developed quite a bit over the last 10 to 20 years in terms of processing capability. I remember early in my career, we talked about digital output image sensors, and that was a new thing because all of our image sensors in the infrared world were analog output. And it was a big deal because we had an analog signal processor that we needed to convert that into the digital domain. And if you could put that on your image sensor itself, that got rid of a lot of electronics interfaces issues. We got up to 14 bits on our column analog to digital converters, and that was a great thing. So if a digital output array is a good thing, then more is always better, right? So we've moved to per pixel digitization. And that was the digital pixel array that you see on the top right side of this chart. In that case, you could actually digitize on a per pixel basis, and you could get 16 to even over 20 effective bits of dynamic range. And you can get either low noise from that capability, or you could do charge transferring from pixel to pixel. And this actually gave us some very simple processing capabilities that people started to implement, things like up-down counting, things like edge identification, and then doing pixel-to-pixel transfer of orthogonally of your image sensor information. And that kind of gave people an idea of what they would do with a more capable processor at the readout integrated circuit level. And this led to a couple of more recent DARPA programs. Reimagine was all about taking essentially a FPGA that normally sits in the warm space and put something like that similar into the cold space and make that into a processor capability that is right there at the readout integrated circuit level. So we had a 3-tier architecture. We had the absorber, the sensor interface layer of the readout, and then a digital fabric that gave us multifunctional capabilities. And that was a great program to show what was possible if you had a processing capability at the readout integrated circuit level. The one thing that was a challenge, though, that the program highlighted was that power consumption becomes a big challenge when you do this. People have cryocoolers that they're trying to keep their detector absorber surface cold, and it was a technical challenge to have too high of a power on that cold stage. So that got people to thinking, how do I evolve that to put that kind of processing capability onto a readout integrated circuit without having to do a massive amount of cooling for that part. So new ideas have come in since then. A recent program that's still ongoing is the FENCE program, and that is an event camera. And this is also a 3-tier layer, which has an absorber, a readout, and then an embedded processor. But the idea of the event camera is that you would have far fewer events than if you're just looking at a wide area persistent surveillance scene, you would be able to identify only the events of interest and only process and data transfer those off of your image sensor. So that is a great enabler for power consumption, solving the challenge that Reimagine highlighted, and then also a huge latency enabler. So I think that there are potentially new ideas in this area. You can see how the readout architectures have become increasingly context-aware over time. And I think that there is more to be, more information and more capability that we could have at the readout integrated circuit level to become more and more context-aware. Okay, so let's talk about optics next. This chart just shows that today's optics have very limited context awareness. Now, you can get tunable optics by doing a couple of different things. On the left side, you can see the NASA APS Glory mission. They have multifocal plane array apertures. So you can see they get tunability not through tuning anything, but they just have a different image sensor that's collecting different information on a frame-to-frame basis. So you get it fast, but you don't have any adjustability. On the right, you can see filter wheels. That's a JWST NASA filter wheel. And you can see that you can have a bunch of different filters and one image sensor behind that collects all this information. And you could tune by changing the filter that is covering your image sensor. But that is slow and it is bulky, and it ends up not maybe meeting the goals that we would like of trying to get to an outcome from our image sensor that our signal processing people would be happy with. The other thing that's limiting about this is that you have predetermined spatial and spectral elements. So by the time the JWST is launched, you can't go back and change what those filters are. So if you decide you want something new, you got to send something new up to space. Okay, so how do I think we're going to solve this problem? We have tunable optical materials, and that enables a fast multifunction aperture, analogous to what you saw on the previous slide, but with that quicker, better outcome that we're looking for from our signal processing. Now, there are two different general categories, I would say, of tunable optical materials. You have metal lenses. These are a flat optic. They generally give you enhanced field of view, and some people have even found ways to tune them to get a limited zoom lens capability out of them. So this would be a great enabler to making your image sensor more context-aware. You also have metasurface filtering and shuttering, and there are capabilities there that allow you to have a fast index of refraction tunability. And you can also tune these things with multiple mechanisms. So whether that be light tuning or a thermal tuning or some kind of a bias. And that would allow you to go get those different spatial and spectral elements that you want from your image sensor on a frame-to-frame basis to be tunable. Now, today, tunable optical materials are fairly tunable, but maybe over about an inch, and I need them to do more like a mile of tunability. So the technical challenges that we see associated with these tunable optical materials is there's only a limited set of switching mechanisms. We also have bandwidth limitations. They're tunable, but they're not necessarily tunable over large enough bandwidths. They all have losses associated with them, very similar to optical elements that you would see in any image sensor. We have immature algorithms. If we're going to tell the image sensor what to acquire, we have to figure out kind of how to do that. What algorithms would we actually want to reach back into a camera and tell us what to obtain? Scalability. Some of these are made with very slow processes, so making a very small meta-surface optic is practical and feasible, but making larger apertures that we would need for military or long-distance sensing applications is a challenge. And then many infrared optics don't sit at room temperature, and they also have to be out in the field for many, many years. So there are a ton of technical challenges associated with tunable optical materials, but I think that in terms of image sensor context awareness, this is probably the biggest impact area that we could have to truly make the image sensors more context aware. Okay, so if we had tunable metasurface optics, what would we go do with them? I mentioned previously region of interest filtering and shuttering that you can see on the top left. People today use polarization in various bands to get 3D facial recognition that is passive. You can do passive ranging with a fast update rate. And then many of these tunable materials are much smaller and lighter than their traditional optical material counterparts. So improved size and weight of optical systems is a pretty big impact by using these tunable optical materials. So these are the things that I have thought of, and I would challenge you out there to go think about what you would go do with these materials to make image sensor more context aware. Okay, so just to summarize what context-aware imaging is and isn't. So what I really would like to go do is reduce the large amounts of image data that we have while maintaining all of the information that we get from an aperture. I want to enable new functionality, and I want to be able to do that while maintaining or improving the size, weight, and power of the system. And we want to be able to also capture information passively that may be used to be captured actively. It is not an incremental progress idea. We want to, your next step in absorbers, maybe the next step in readouts or some incremental progress in that area is probably not going to be all that interesting to me. And I'm also not particularly interested in traditional optics. So I'd like for people to bring me their ideas in this area, and if you have any interest in it, and happy to please reach out and happy to have a conversation. Thank you.